for Marion to invite us. So, Yinzhi and I are excited to present here. Like, we work very closely on several projects. One of the main projects is funded by the Johns Hopkins Institute for Assured Autonomy. Yinzhi is going to say a few words about that later, but essentially it's a new institute. It's been stood up like 2 years ago, and is looking at all issues that are concerned with like trust in AI, trust for the AI, and assured autonomy. So specifically, today, I just wanted to first highlight the folks that we're working with. Of course, like Yinzhi Cao, who's a professor in computer science department, myself, and also of other people. I'm going to admit some people in the room here. Most of other people also, both at the Johns Hopkins Applied Physics Lab. We have a student from UMD, incidentally, and other folks at Queen's University, Duke University, and as well as some folks over the School of Medicine. We don't have any conflict of interest disclosure. So anyway, so what we're talking about here is like two of the important topics in trusted AI, which involves robust AI, explainable AI, trustworthy AI, and etc. So this is one way of cataloging, the different areas of research currently, and fairness and privacy and safety really figure as two of the main concerns that people have. Of course, everybody has read many items in the news concerning like fairness as well as privacy issues in AI. So before we start, we wanted to talk, at very broad level, what are the problems we're going to try to solve here and address. So regarding bias in AI, and most of the talk I'm going to present is going to concern AI diagnostics and AI dedicated to healthcare. And so in that context, and you can see some images, for example, here of like retinas for which we might want to find if the person, the individuals has retinopathy, and people who may have some different type of skin lesion. And immediately we can understand that, ethnicity, other factors might have a strong incidence on the presentation of the images. And then we can ask the question, is there like equality in terms of diagnostic accuracy? So I'm worrying about the utility as a whole, like the diagnostic accuracy as a whole. But also we are concerned about the fact that this accuracy should not be very different across different protected factors. And by protected factors, we mean, gender, race, and age primarily, but there are other protected factors. So you see me use the term protected factors, protected attribute, sensitive factor, or attribute, etc., interchangeably. But one thing I wanted to highlight is that, nomenclature does have an importance here, especially like with regard to like usage of terms, like such as gender, sex, race, ethnicity, origin, and etc. Like there is a sort of an importance, and those nomenclature do matter. For example, in the realm of healthcare, like the American Medical Association, the AMA, has issued guidelines in the past couple of years on how to use those terms, and those guidelines have been changing, every year. So, it shows you that, those things not only are important, but also they are so changing. So we have to be very careful in the way we use words. With regard to like privacy, and Yinzhi is going to talk about that later. Among the different issues in privacy, we are talking mostly here in terms of like membership inference attack, and Yinzhi will describe more in detail what it is. So first we're going to talk about fairness, and then we're going to talk about privacy, and let's jump right in. So the main application domain I'm going to talk to you about is healthcare. And within healthcare, I'm going to give you a lot of examples of retinal disease. So I thought, like, let me give you like just like a quick rundown of what are those main diseases. So in the realm of retinal disease, like two of the important diseases are AMD, which stands for age-related macular degeneration, and we're going to see some examples from that. And the other one is a diabetic retinopathy, and it's abbreviated as DR. So on the left, you have an example of diabetic retinopathy, and you see those lesions here. These are called hard exudates, and these lesions and other, image marker when appearing in the macula are signs of diabetic macular edema. And DME, is something that fortunately can be treated in most situations, but it does affect central vision. Okay? And why is this important? Is that pretty much like 500 million people in the world, more or less, are affected by diabetes and are liable to develop this type of manifestation. On the right here, we have one case of age-related macular degeneration, AMD. with geographic atrophy. Okay, so you see like this lesion in the center, again in the macula, and likely the person here is like legally blind. So the person has lost central vision, which is key to accomplishing tasks such as reading, recognizing faces, etc. Unfortunately, this type of disease is not treatable, but it's still important to do diagnostic and characterization of how severe the disease is, because treatments are being investigated right now. So in order to be able to establish the efficacy of those treatments, we want to develop AI tools, diagnostics that can establish the severity of this disease. So our goal is, the concern we have is that these diagnostics have to be fair, meaning that the gap in, accuracy between different type of population, let's say African American versus Caucasian, is as small as possible in terms of accuracy gap. So a quick review of terms, I'm sure like during this seminar series, you've seen people present over and over again, what are some of the main used definition of bias. And, I'm just going to mention them to make a comment on that. I'm not going to go into like an exhaustive explanation of all the possibilities. There are literally dozens of possible objectives that you could have in terms of like stating what mathematically fairness means. But essentially, if the protected factor, like the protected attribute is S, Y hat is what you want to predict, for example, the presence of diabetic retinopathy, and Y is the actual, underlying value of this variable. Then one of the widely used, definition of parity or fairness is demographic parity, which states that the probability of Y hat, is essentially independent of the sensitive factor. And so, this makes sense in situation for example, for like a loan application that you want to say that as a goal at the end, you want that you give loans at a rate which is independent of the underlying gender, the underlying age, and the underlying race, ethnicity, origin, etc. What makes sense, though, in the context of healthcare is to use this definition, equality of odds. And it does the same thing, but it conditions it on the actual value of Y. And so what you have here is like condition on Y, the prediction on Y hat is conditionally independent on S. And so this is interesting because this conditional independence, condition Y, also states that the errors, that you may make, think about like a binary classification where you want to decide whether the person has or has not diabetic retinopathy. So like the false alarm rates will occur at equal rates. Irrespective of the sensitive factor, the non-detection will occur at the same rate. Sensitivity and specificity, which are often used in medicine to characterize performance, identical or as close as possible, depending on the different, demographic factor. And so what we want is like to decrease the gap between those values. There's also equality of opportunity where you do the same thing, but you do it for a specific value of Y. But anyway, the takeaway from this is two things. The first takeaway is that most of this definition states something about equality of performance, but they do it via some sort of conditional independence. And so, because of that, it's possible to devise methods that go at the conditional independence directly. They do in an adversarial fashion, they try to develop a representation of the data, which is immune from or is devoid of like sensitive factor information. And, one of the reasons why Yinzhi and I are working closely together is that you can imagine that when you want to make yourself independent of or unaware of, or develop a representation that are unaware of certain sensitive information, this sensitive information may be catering, or orienting or focused on things that you want to forget because of fairness reason, but it may be things you want to forget because of privacy reason as well. So you can see that, the fairness and privacy really, based on these factors is really like joined at the hip, as two issues in terms of like the way that they are being attacked. Not always they're being attacked, but some ways they're being attacked. Okay, some causes of bias is that there may be some inherent dependency or correlation between prediction and protected factors. Another big cause of bias is that, frankly, you just don't have enough data. So we have a lot of data, for example, on, retinal diseases or on skin diseases for Caucasian. You don't have as much data for African American, and perhaps maybe, not in all situations, this results in the, unbalance, results in having less performance when applying the diagnostic tools on African American than Caucasian. It's not automatic, sometimes we we may have data imbalance, which may not lead to bias, but it's one of the causes. And of course, like one of the main causes of bias is basically like AI perpetuates, like by design, possible bias by humans. Just going to give you an example. For example, Obermeyer et al. 2 years ago, developed a study where they demonstrated that a tool that is now being deployed to predict the need for healthcare is biased against African American. So what is meant by that is that if you take two populations, one Caucasian, one African American, that have the same underlying risk, this tool predicts that there is a higher need for healthcare for Caucasian. And the reason why this happens is that the proxy, essentially the measure that it used for predicting this, which was the past cost, incurred by those individuals for healthcare, was biased itself, right? Because like Caucasian were using more healthcare, so it was predicted to use more healthcare. So you see, like by design, humans sort of introduce bias in the algorithm just by the design of like the proxy or the metric. So that's one of the ways it can happen. All right, continuing, and I'm gonna go a little bit faster here. But essentially, like a lay of the land, I'm pointing to a couple of survey papers at the end. This is one of them. And one of the things, I don't agree with everything that's made, but it's a nice paper. And one of the things that's, nicely argued here is that, generally speaking, there are methods for debiasing or for fairness that do something to the training data. So they are called like pre-processing method. There are in-processing methods that do something to the model, and there are post-processing methods such as like recalibration. And what we're going to look at is mostly in this realm, of doing intervention in terms of the training data. Sometimes we don't have enough, how can we use generative methods to generate more data? And how can we use adversarial method to make models more immune to knowledge or forget about knowledge about sensitive factors so that they become more fair, okay? All right, so without going into the details here, like the first method I'm going to talk about, we call it like latent space manipulation. We're doing some sort of like intelligent augmentation that creates more data of a certain kind that we are missing. Let's say, for example, diabetic retinopathy for like African Americans might be missing, and then this is meant to mitigate the imbalance in the training data. And the second method, like I mentioned, is an adversarial method. I'll talk about it a bit later. So if we wanted to generate more data, first of all, we could acquire more data, but sometimes, we have retrospective studies, we cannot acquire more data. So we turn to like synthetic methods to generate more data. That's what we're looking at here. And so like, some go to a very successful algorithm that have been used in terms of generative models are, for example, StyleGAN or BGAN, etc. And the way it works, I'm not going to go into details of StyleGAN, but the way it works is that it's this algorithm whereby we have a fully connected network that maps from latent space to another style vector here, which is using and injecting into a process by which we sort of have this like multi-resolution process whereby they are able to generate those very high resolution images. There's some possibility of mixing the style vectors and generating new data that are a mixture of existing data, but it's not exactly what we want here, like in terms of generating new data, because we would like to control exactly what we get. We don't want to get just a mixture of folks, as in style mixing. We want to get exactly what we want. And what I mean by this is that, if you use StyleGAN, for example, and travel in the latent space, you get like beautiful and realistic images like this, okay? And so you get images of like different vasculature, different people which don't exist. You get different type of like, lesions that you can see, like some that look like geographic atrophy, some that look like drusen. This is like all trained on age-related macular degeneration. So it's all good, but like I said before, like the problem is like it might not generate exactly what we want. What we want, for example, might be Caucasian retina, which has type 1 diabetic retinopathy or type 2 diabetic retinopathy. So what we want instead, we want to ask the question, how do we travel in an optimal way in the latent space so that we generate exactly what we want? And for example, okay. And what we want is something like this. Is like we start with an image here of an African American, and we want to travel in the latent space in order to generate images of African American with the right lesion and the same vasculature. We want to minimally affect the vasculature, so we want to keep things invariant, but have like a credible lesion that we can turn around, and use this thing to train or classify if we didn't have enough images of this type, African American with age-related macular degeneration. So this process is a process of doing a gradient descent. So we are traveling in a manifold corresponding to this latent space. And what we're doing is that we're establishing a classifier for the attribute existence or non-existence. Like here, for example, if the attribute is like we want to impart lesions that correspond to macular degeneration, so having versus not having it is a classifier that we can train on. And then after that, we basically do gradient descent on the loss function of this classifier. And essentially, it's a gradient descent on the log likelihood on the presence of the macular degeneration. So therefore, on the presence of this lesion. And doing that, we're able to generate images in a direction where we only, optimize the presence of these lesions and don't modify, hopefully don't modify anything else. So these are examples, again, going from images of African Americans to African American which have now not age-related macular degeneration but diabetic retinopathy. So you see like those hard exudates here, and same thing on the right here. And the same principle can be applied on IPACs. I'll show you some example. This is actually like Celeb A, like a data set that you're familiar with of celebrities. Not too many like elderly females. So for example, if we want to have a task of being able to classify something irrespective of age, then we may want to generate more exemplars of females that are older, or here, like for example, individuals that have darker skin, for example. So the same principle can be done. We're trying to minimize the alteration of the face, but maximize the addition of this attribute. More examples here of like transforming an image here. So in time, we show like transformation of images from Caucasian to African American and vice versa, imparting macular degeneration using this method. This shows that if we start with the baseline method, which is biased here, so we have accuracy for detecting age-related macular degeneration, which is 80% for Caucasian versus 62% for African American, we can reduce the bias to a large amount. And not only reduce the bias, but also like overall increase the utility, as measured via those different measures, like accuracy, sensitivity, specificity from the baseline method to the new method, which use this augmentation and domain adaptation. But what's interesting is that in general, we have a tension between the overall accuracy and the utility of the method and then the accuracy gap. So as you see here, like we start with a baseline, which has the overall accuracy at 66% and quite a large accuracy gap between light skin and dark skin individuals. So this is diabetic retinopathy detection, 12% accuracy gap. And using one flavor of the latent space manipulation method I mentioned before, we can reduce down the accuracy gap from 12 to 7.5%, so it's more fair. And this increases also the overall accuracy. But if you further reduce, using another method related to what I described before, the accuracy gap, now you can go down to 0.5%. And so there you have like, incidentally, like a decrease, it's better on this one, but you have a small decrease in overall accuracy. So what it suggests is that there is, even in this approach, there is sort of a trade-off between overall utility and accuracy. So it begs the question, like, what are the right metrics to measure that? We can use joint metrics, the same way we use like PD and PFA, for example, in an ROC curve. We can do the same thing, and we can measure the overall fairness via some sort of gap in accuracy, UCOF1 score, and the overall performance. We can, do like curves, and we can also do single metrics, like, we can use a Pareto curve. We can look at the minimum overall subpopulation of the accuracy. That's sort of like a Rawlsian view of things, which comes from Rawls, an economist at Harvard in the 90s. And then we can also use some sort of like weighting of the two metrics. Like if we go from a baseline system to a device system, what was the change in terms of like decrease in the accuracy gap, and what was the corresponding change in overall accuracy? You can balance them, and you can see what you get. So like the entire, I guess like the thread line here and like the subscript is that how do we measure that something is good overall? And you can see immediately what emerges is that if you have to consider both the utility over the entire population and then the fairness, then it becomes the fact that we as engineers, we can design metrics, but we really need the help of ethicists, philosophers, policymakers to be able to decide what is the right metric. In particular here, what's the choice of alpha. So very quickly here, like what we've done, in addition to doing this this augmentation method, we paired it with an adversarial method, which consists of having basically two adversaries. So here, like you have the input X, which is the image, which, via an encoder leads to some sort of representation. And we want to develop a representation that is fair. So what we're going to, and useful, right? So we're going to have like a player that's going to infer Y hat, whether the person has a disease or not, for example, and based on this representation. But then, this person is going to find an adversary with whom it collaborates. The adversary is trying to estimate at best S hat, this adversary is trying to estimate what is the underlying value of the sensitive factor. And the main player is trying to minimize the ability of the second player to do that. So you see that we have an optimization on objective function for the main player to maximize the utility, the determination whether the person has diabetic retinopathy, while denying the second player the ability to guess the race, origin, gender, and etc., which ends up at the end to have like something which is fair and useful, to some extent. And the balancing is beta again here, which poses the question, how do you balance beta? And here, like again, we defer to our friends, philosophers and ethicists with whom we are collaborating at Johns Hopkins. But then, overall, you can see, like, when we measure the performance of a baseline model versus a model that uses this sort of intelligent augmentation and this adversarial, blindness that I just mentioned before, removing the information in the representation about the sensitive factor, then the combination of the two leads most often to like the best outcome. Not always, but most often. So this is applied on the diabetic retinopathy. We have similar results that try to predict age and takes gender as a sensitive factor. So anyway, that's sort of like the lay of the land. So we are continuing down that path. Again, like the big comment here is that we as engineers, we can design loss function, but in the design of those loss function, and they can get quite complicated. And in particular here, there's the simple one, right? We just have two factors, overall utility and then fairness. It's really like we have to turn to like more and above and beyond our community here, looking at ethicists and policymakers as to what good looks like, and what good looks like really depends on the specific use case, right? Also, just some thoughts. When I was telling you before that we are trying to generate more data with control attributes, one of the things we are looking at is this thing called like InfoStyleGAN. So basically, it's like a mixture of like InfoGAN and StyleGAN, whereby we're trying to establish and maximize mutual information between the latent space, some part of the latent space vector C, and then the output like generated image, so that, and we do it in the context of StyleGAN, so that we can find C being aligned with some semantic attribute of the data. So for example, ideally, this aligns with like, like skin tone and orientation of the face, and the presence of glasses aligns with, the variables in C, so that then, we can turn around and generate more data of the specific kind we want. And, one of the big question is like being able to control in GANs while being able to disentangle. And, there's some deep relationship between control and disentanglement that can be described in information theoretic terms that, is beyond the scope of this talk, but these are things that are worth investigating. In any case, these are, collaborators, again, some papers to look at, and more papers to look at in terms of like, past surveys. A couple of ones that I highlighted here are really nice ones. So with this, I pass on the baton to my collaborator, Yinzhi, who's gonna talk to you about the issues of privacy in AI. So Yinzhi, I stop sharing. Okay.
Okay. Yeah. Thanks, Phil, for the introduction. Let me start. Okay. Now you can see my screen, right?
Yes.
Okay, thanks. Yeah, so I'm going to talk about the privacy issues in artificial intelligence, especially being applied to the healthcare problems. So as we can see, like artificial intelligence has been used in different areas. We said like the medical diagnosis, like the retinal disease, skin disease, and also language recognitions and self-driving cars and social media. So they're all different scenarios. So it's very popular. However, one of the problem in the artificial intelligence and machine learning is that it's always facing like a privacy issues. So specifically, the privacy problem we're looking at in this talk is called a membership inference attack. So what it is that say you train a machine learning model. So you have the training data and you get a model, and then when you feed new data into it, you get predictions. So however, what an attacker can do is that it tries to input, say this is a retinal image, it feed into the model, and then it obtain its output, which is a probability of vectors. So in specific cases, we have a retinal disease. So 0 means this is a health, retinal image, and otherwise have some degrees of disease in different severeness. So based on the output of this machine learning model, the hacker can do is try to infer whether this data records belongs to the training set. So that's what we call membership. So this is a privacy violation because, say, for example, this specific patient is being diagnosed in a certain hospital and is supposed not to be leaked out because it's a violation of HIPAA. However, that attacker can launch this membership attacks and try to leak the private information from the model, and so that is what we see called privacy attacks in machine learning. So there are some prior works on a membership influence attack, specifically in 2017 in IEEE Security and Privacy, the Oakland. People proposed more like the first modern membership influence attack. So how it works is that say you have a target data set and you train a targeting model and you can test the targeting model. So you get some query data, so which is attacker has, it tries to goes into the target model and then to give the probability score. So how do we categorize what is a member or non-member? So how it works is that in the paper, they propose that you have another surrogate, the local data set, and then you use this surrogate local data set to train another shadow model. And then based on the shadow model, you will get another list of probability scores. Some of them are we call members, that means it's in the local surrogate data set. And some of them we call non-members, so they're not in the surrogate data set. So, and then based on this, you have the ground truth, and then you can train an attack model. And then after that, when you feed the target models output into the attack model, it can do a classification, say, okay, whether this is a member or non-member, this is a attack. But the problem here is that, so what if the shadow model is not like the target model, because that the surrogate data set may be different from the original data set, and also the model use different architecture. What we do is here we show a result. So we look at two type of data set, one is CIFAR 100 and the Celebrity data set, and we use a target model as ResNet 50 or ResNet 101, and then we use different shadow models. So you can see if we use exactly the same architecture with the target model, the attack F1 score is actually very high. So it's above 90%. However, if we use the model that different, for example, in this specific case, when we use VGG 16, and the attack F1 score will drop significantly. So here's 20% differences between the ResNet shadow model result and VGG result. Similarly here, if you use DenseNet, and then the attack F1 score is dropped to 30%. So it's the big drop of the attack F1 score. So then the question comes, so how are we going to deal with the problem? So, I mean, it's there. The shadow model could be very different from the target model. So the answer will be we should give up the shadow models. So how we're going to give up with the shadow models is that we design our attack, which is called a BlindMI. So this paper is published in NDSS this year, 2021. So still, we have the same thing. We have the target data set. We train target model, and when the attacker tries to query the target model, they get their probability score. So instead of using the shadow model, so what we do is that when we have some data set and we can transform some data set into a non-member data set, because think about the the image space. So it's very easy to get like a non-members rather than members. So just do some like random generation, or you just do some like transformations, like adding noises, you can get the non-member. And then you use the non-member dataset to feed into the target model, and then you will get a list of probability score that you know they are non-members. Then you will compare with the result you get from the query data with this like non-members probability score and see if they are similar. If it is similar, and you will consider it as a non-member. Otherwise, you'll consider it as a member. So very simple. So the advantage is there's no target models, and therefore it will get rid of the subtle differences that we get from the shadow model and the target model. There are several variations of our BlindMI. The first variation is what we call BlindMI one class. This is actually another baseline that we try to compare with. What we do is we train a one class SVM model on non-member set. I mean, it's in the naive way where you have just one class and you want to see the performance. So this is BlindMI one class. And another is actually the core contribution of our work is called BlindMI diff. So what we do is we propose a novel approach called a differential comparison. It tries to differentially compare two sets in hyperdimensional space and then gradually decide whether those samples are member or non-members. So specifically, so this is the overall architecture and explained our core idea. Assume we have so here is like a set that contains mostly of the non-members. And here is a set, it's a target set. And so what we call differential comparison is that we differentially move samples from the target set to the non-member set, and then we compare the distances between those two sets. So as you can see here on the left side is the non-members, on the right side is members, and this curve is a decision boundary between member and non-member. So when we differentially move one samples from the target set to the non-member set, we observe the distance between those two sets. If the distance is increase, so we will know that, okay, most likely the things we moved to the non-member set will be a non-member because it pushed the target set further to the member space, and then pushed the other set more to the non-member space. It increased, and we know this most likely will be a non-member. On the other hand, if the distance between two sets decrease, and we know most likely this is a member. So this is just like one iterations we're going to do. So eventually, that means it's the intuition. So in the implementation, in the design, so what we do is that we'll do it iteratively. So we first compare all the samples in the target data set, and then we merge it until that's no set will improve or decrease or increase the distance, and then we recalculate the distance based on the new samples, and then we do it iteratively until it converge, and then we can make a decision of whether each data samples is a member or non-member. So then we look at the main result of the work. What we do is that we perform our attack on several data set. So this is all the data set that we included, including it ranges from an image data set to some a non-image data set, the purchase 50, which is the shopper histories. And the number of classes also varies. So in the cases like IPAC, it's just have 5 classes. In some cases, like 200 has 200 classes. The resolutions also changes, and the trend data set also, the size of the trend data set also changes. So here we take a look at the first question is that whether the distance indeed change. So here we would like to know that there are another two variations of BlindMI dash diff, which we use the differential comparison. So the first one is that we use a non-member data set. Another is we do not use a non-member data set. In terms of we do not have a non-member dataset, we still have like two classes. We can roughly divide it into two classes based on the clustering or based on a single like threshold based on the loss function value. And then we can divide them into two sets, and then we can still perform the differential comparison. So in the terms of without, that is the case that we do not have a like a non-member set. And in case of with, is we have a non-member set, but non-member set is being generated by different techniques. For example, we said like random generate image, or we can transform existing images into non-members. So in both cases, what we do is we look at the number of like a move per batch, and we look at the distance. As you can see, the distance indeed increased on different data set. So here you can see C400 actually increased the most, and in many cases they all increase. So that means that that's very effective in terms of our differential comparison. And then we look at a comparison with state-of-art membership inference attack. So here, as you can see, we look at several different settings. So we have the blind and the gray blind setting. We also have a black box and the gray box setting. So the differences between the black box and the gray box is that whether you know the specific architecture. So as we can see, in the gray box, that the attacker, the adversary, knows the model architecture, like DenseNet versus ResNet, and the differences between the blind and the black box is that whether you know the ground truth label of the image. So in many cases that the label are easy to obtain, but in some cases it's hard. For example, like the IPAC example, you need a physician to really diagnose this and see whether they have a disease. So the label are not that easy to obtain as well. So the first observation we look at this like a table is that the shadow model indeed, as we said, have an impact. So you can see in some cases that this specific loss threshold attacks, that the differences between the black box and the gray box in terms of whether they know the architecture have like 28.2%. So in many cases, in some cases in birds, it's even have like 38.5%. However, like in our BlindMI case, you can see that no matter you know or not know the architecture, and the result is always the highest. And another observation we have is that in 4 different settings, no matter you know or not know the architecture, so even if that in the cases that attacker know the architecture, that the BlindMI still perform the best compared with all the state-of-art attacks. So you can see that the F1 score is always, the bold one is largest of all the cases. So it means that the differential comparison actually is very effective in determining the member versus non-members. So here we listed actually 6 different of state-of-art attacks. Some of them need shadow model, some of them actually do not quite need shadow model. So the NN, the top 3 NN, so those are we talked about the neural network based attacks, and then we also have top 1 threshold based on just a simple threshold to decide whether this is a member or non-member. We also have the loss threshold and the label only. Loss threshold is the attack that try to calculate the loss function, and then if it is larger than a certain value, we consider as a member, otherwise consider a non-member. So those are just simple decision boundary. So this are not worse than BlindMI. And label only is just based on label, consider the label and prediction and decide whether this is a member or non-member. So to summarize, so if you look at this table, we know that BlindMI always performs best compared with existing attacks. And then we look at another function, so another graph to see if existing defenses is effective in preventing BlindMI. So specifically, we list 4 different defenses. So the first defense is the MEMGuard, which is a CCS paper. So what it does is add this carefully crafted perturbations to the target model's output and turn it into adversarial examples. So basically is that it does not change the label, but it changes the output probability. So it looks like a non-member. So this is the idea of MemGuard. So if you look at the result, that the blue line is BlindMI always perform the best compared with existing like attacks in terms of defense, and so the accuracy is actually very high in this specific case. This is our CHM-NIST. So that's for MemGuard. So it does not actually decrease the Inference score of the BlindMI. And then we also look at the second one. So in terms of performance improvement, actually BlindMI outperforms existing work to 5% to 75%. And then we also look at the differential privacy. So this is also de facto defense of any privacy attack. So here you can see that the BlindMI is the blue line, so it's almost decreased a little bit as the privacy utility budget increase. On the other hand, many other attacks actually decrease a lot. So that when you do differential privacy, so DP-Atom is a paper that's also published in CCS, try to add differential privacy to deep learning system. So our BlindMI outperforms to like 8% to 59%. And also look at another approach is the MMD plus mix-up. So basically what the paper does is adopt a maximum mean discrepancies to reduce the gap between the softmax distribution on training sample and validation set during the training. So similarly, our BlindMI outperform existing attacks from 5% to 75%. And lastly, we have another defense. It's called adversarial regularization. So what it does is try to model the membership inference attacks as a regularization terms to be used in regularizing the training of the targeted model. Similarly, this is another CCS paper, I think 1 year before the MemGuard. So it outperforms like a 10 to like a % to like 60% in terms of like F1 score. So that to summarize, BlindMI compared with all existing attacks is very effective in like bypassing style or defenses with a reasonable privacy to utility budget parameter. And after that, so we're looking at another matrix. So in the previous all the settings, so what we're looking at is that the target data set that we fit into the BlindMI model, the ratio between non-member and the members is 1. I mean, half member, half non-member. So some people working the membership first attacks always argue that this is kind of like not practical, because in the real world cases, most of the sample you get is actually non-members, and the number of members are much smaller than members. So in this case, that the F1 score will actually drops when you have like much more non-members compared with like members. So here, what we're doing is that we compare the like F1 score of all different attacks with BlindMI when we increase the non-member to member ratio. So you can see that the largest one we get is like a 39, means like 39 non-members compared to 1 member. So all existing attacks, so they most likely drop, and they drop in the same ratio or mostly. So you can see that when it exceed like a 13 or 14, and the FS score is already lower than like a 50, it's more like a random guess. So it's very non-effective. However, even you increase it to 39, that the F1 score of like BlindMI is like still over 50. So a little bit over 50. So that means BlindMI is very effective when we used in real world case. So specifically, it outperformed like a 35%. You can see that here is a large percent of differences between BlindMI and StarWalk. And we also look at another matrix, which is the FS score versus number of classes. So specifically, what we use is we use CFAR 100, and we can like increase the number of classes from like 2 until we reach 100. CFAR 100 is only 100 classes. So obviously the number of class increase and the attack performance, which in terms of FS score also increase. So this is aligned with the state of art, like researching membership inference attack. So specifically that people argue that membership attack is in many cases being caused by like overfitting. So when the number of class increase and the probability of overfitting will also increase. And that's why that you can see the FN score of the attack also like increase. So in terms of the performance, so BlindMI actually outperform existing work in terms of like 5% to like 30% in the best cases. So that's BlindMI. So in the previously what we just talked is a attack. So this is the BlindMI attack that we introduced. And then the next question is that how are we going to defend against this membership inference attack? So here we introduce approach. So the high-level idea is like this. So we use the GAN to generate the generative adversarial network, generate synthetic data samples, and then we use synthetic data samples as part of the training data, and then we generate a model. And when you really do the inference, and you are looking at the not the original data, but you use the synthetic data. So specifically, the architecture of this defense looks like this. So you have a private data set, which may come from medical data source, and then you fit into a generative model, and that will generate the synthetic images. We have both synthetic images and also the raw images. We make sure those images, and then we add additional like defenses, and together with training data, and we train a classifier, and then we goes to this classifier, and then we can launch existing like membership attack, and we look at the performance of the various membership attack. So here are what the synthetic data looks like. So on the top is the real data. So this is the healthy real world data. This is disease real world like retinal data. So as we talked like 0 to 4, like 0 is health and otherwise with disease. The examples are from the producer, and here is how we produce. You can see that this looks like the real images, and you can see this is the generated data. And then we look at the result. So here is the specific result. We take a look. So we have 3 categories. First is synthetic data only. So you can see that in the black box and the gray box attacks, the F1 attack accuracy or like close to random guessing. And then we term of like defense, if there's no defense, and the defense with the MAD plus mix up, this is one of the defense we discussed. So the accuracy is like 33.3% for the task. We also look at the different the mixtures in terms of synthetic and real data. So we have the different percentage of raw data access. We range from 25% to 75%, and we look at the term of accuracy. So the accuracy actually increase in terms of the introduce of real world data. And if you have only real world data, you can see that the accuracy is actually the highest, but the attack accuracy is also high. In the cases like loss threshold is have like 61.8% of like attack accuracy. So this is the result against attack. Lastly, I want to just use one slide to introduce a little bit of our new institute at Johns Hopkins, which is called Johns Hopkins Institute for Assured Autonomy. It's IAA. So that's what Phil and I are coming from. The vision of this like IAA institute is tries to drive a future where this autonomous system are trustworthy contributors to society. So we have 3 major pillars in this new institute, which are technology. So we want to like a design, like things like we presented today in terms of making the autonomy assured, in terms of privacy, security, and all other effects, in terms of an ethical, reliable part into the like assured autonomy system. We also have the ecosystem. We want to build an ecosystem involving all parties into the system. Definitely also have the policy and governance in terms of like how the government will play a role in this assured autonomy, especially self-driving cars, and also in terms of healthcare. This is the new institute at Johns Hopkins. So we have a website. So it's ia.jhu.edu. Feel free to look at our website and take a look at the different projects. So we have like a 10 a frontier project. So feel free to go to our website. So in conclusion, so what we do is that we addressed the dual problem of bias and privacy in AI. So in the bias, we use GAN to generate different type of synthetic data to make sure that the model is less biased in terms of race, age, and in terms of privacy, we look at the membership influence attack, and we show that both in terms of attacks, we invent a new attack, BlindMI, and we show that it's effective and outperform all the existing state-of-art attacks, and also we can bypass existing defenses. Also come up with new defenses in terms of generating synthetic data, and show it's effective in terms of defend against attacks. And our implementation, especially the BlindMI part, which is the privacy attack part, is open source. This is our DSS paper, so feel free to use our source code at this URL. So yeah, in the end, thank you. So if you have any questions, feel free to ask us. Again, this is the Johns Hopkins Institute of Autonomy.
Thank you very much. That was great. Let's thank both the speakers for the talk today. Thank you for joining our seminar. Anyone that has questions, feel free to unmute yourselves now and ask them. Okay, well, while we wait for other questions, I have two questions. So the first one, in terms of your generative model for constructing fair data sets, so you want to be fair with regards to some attribute, let's say race. Can it handle combinations of attributes? So say you care both about race and income level?
Yeah, it's a good question. Yes, it can. In principle, it can. However, we have thinly tested it. We did a test recently to look at celeb A, where we had the prediction of age, and if I remember well, we took like gender as well as ethnicity as being the sensitive attribute. And so it seems like it works. And the reason why your question is important is that when we go down the path of like taking the combination of the different sensitive attributes, then we are more liable to fall into those situations where we don't have at all any exemplars of that. So for example, if you wanted to say that you're looking very granularly at how well am I doing at detecting skin diseases like tinea corporis, for example, or erythema migrans or whatever, or like diabetic retinopathy. But then you say, what I want to make sure is that if I take the cross of the gender and the age and the ethnicity, and then across all of this partition of population, then I want to be fair. Then when you're gonna train for that, if there's any sort of imbalance, it might arise very easily, right? Because taking the combination is likely to reveal that for a specific combination, let's say like older, African American women, there might be a paucity, there might not be enough exemplars in celeb A, for example, or or in IPACs. So it's a very important question. Yeah, and so we've seen evidence that it seems like it's helping, but we need more experiments on that. And often, I'll just add one more comment. Often the time, like the difficulty in doing exactly this is that you have to have a data set that has enough annotation, right? So it's not enough to have annotation for the task that you're trying to predict, but you have also to have annotation for like those three types of sensitive factor, and those data sets are not, they are sort of hard to come by.
I see. Yeah, fair enough. Okay, before I move on to my second question, is anyone else having any question?
I actually had a question about that I guess connects the two topics. When you use a GAN or something to generate data to protect people's privacy, and you showed that at least empirically it doesn't affect accuracy too much, I think. I guess I was curious whether it could affect, say, bias or something, like we saw, like style GAN can turn people white, for example. And I was curious whether the training on synthetic data could have similar risks.
Yeah, so it does, in fact. I mean, there are some examples online. You can see that there might be, it's an interesting question. It might be some inherent bias in generative models. You know, they tend to like maybe generate more data of a given kind. Yeah, definitely, yes.
Thanks.
Any other question? Okay, suppose I can quickly move on to my second question. So in the BlindMI attack that you check these distances, what exactly is this distance function there, and have you tried multiple distance functions comparing the two data sets to see if this affects the quality of the attack?
Thanks for the question. The distance function that we used, so actually I can quickly share the screen and show the distance function. So this is the distance function we use. It's actually just the maximum discrepancy distances that we adopt. So like this. And we use the like a Gaussian kernels in this distance function. And we did try like a different distance function, especially in terms of kernel. So we have a table. Let me see where the table is. Yeah, it should be somewhere. We have different like a distance function. This is kernel. You can see with the Gaussian kernel, with the default kernel, they actually in most cases it perform the best for like different the BlindMI like with, and for BlindMI without. So sometimes like Laplacian kernel also works a little bit better, but still like the Gaussian distance perform the best. Look at other distances. If you like linear distances, actually mostly perform the worst in this case.
I see. Thank you. Very interesting.